Yeah, so everyone, welcome to the first session of the network walkthrough. In this series, we're going to, it's mainly going to be Marcelo, who's going to do a walkthrough of our network, P2P network design, and also take a look at some of the implementation in the code. Okay, so I guess I'll just hand it over to Marcelo, and I think today we're talking about how two nodes connect to each other in the network. So yeah, Marcelo.
Okay, thanks for the introduction, Logan. First, I will share some links I want to share with everyone. There is an ongoing effort of writing network specification, which is in an app 69. It's under review. You can check everything that it's written on this render, which is compiled with all the information. Probably we can share it on the. I will share it on the together with the video. So to start, let me do an introduction to how the network works overall, the high level design. Like there is two ways to design, like two main ways to design a peer-to-peer network. One, which is the one used in Ethereum, and Ethereum, for example, is called distance vector routing protocol, which basically for each node in the network, there is some sort of distance between every pair of nodes, and messages are being routed through this network, trying to decrease the distance, and ideally this will get to the destination fast. In Ethereum, this is done with Kademlia. We are doing we are having another approach. We are doing what is called link state routing protocol, which the idea is that you keep each node in the network, keep the full state of the network, like all edges created between every pair of nodes, and are continually updating this view of the network so that they can route efficiently information through it, and maybe trying to creating efficient topologies inside it. So yeah, this is like what is exposed in this Wikipedia page is the overall idea, but right now we have a big challenge, which is that this network is decentralized. So applying naive algorithms, link state routing algorithms won't work. So this is like the overall idea. We won't be discussing today about routing itself per se. We will be discussing about connection between pair of nodes. So I will start by going through the code and discussing each part of it. If you have any question at any moment, just let's try to do this way. Just interrupt me, and I will try to answer any question you have.
And actually, Marcelo, so it seems according to the sessions that Max did on runtime, it seems better that if you just first work through like maybe a reasonable chunk of the code or like whatever material, and then if people have questions, you stop afterwards and then let people ask, because otherwise, from what I heard, it didn't go as well because the progress got
okay.
Let's
do it that way then. Just post the questions in the chat, and I'll eventually come to them and try to answer them, and we can go with that. Okay, so let me share my Visual Studio Code, and this is it. Okay, hopefully you can see the code. So I will start by going through what's relevant for networking. Most of the code regarding networking lives in the chain.
So when you make the window smaller, the text is too small to read.
Okay, what about this? Is it better?
Yeah, better.
I can try to make it bigger, but it may be, let me map. like removing some pieces of, I don't know how to remove this. Okay, let's do it this way and I'll go back and okay, so most of the code regarding networking lives inside the chain networks directory source. So initially, the entry point of the networking of near itself is in of near node and lives in this main RS or libRS that start that call this function start with config, which is basically the function we use to start a node. And this function eventually creates a peer manager actor, but a peer manager actor, which is the entry point for the network. It's worth noticing in this function that we create this network adapter, which is the adapter used for client and view client to communicate to the network. So yeah, we set the network adapter, we set it to network actor, and it's used to communicate between each other. So so let's start going through peer manager. Here inside the network, the three main the logic of the network lives in peer manager RS. Peer manager RS is the one in charge of controlling from high level, you may say, for it's the one in charge of controlling network. PRS is controlling each particular connection between our node and other nodes. That's PRS. And routing RS is controlling the logic for routing messages through the network. It's more low level. So today we'll be discussing peer manager RS and PRS regarding connection between nodes. We are using overall in near for handling asynchronous computation. We are using Actix, which is leveraged here in the network code. Basically, this peer manager actor is itself an actor. It implements actor, and when the peer manager is started, well, initially it's built calling the function new, but when it is started, the function started this call. This is already handled by Actix. So what will initially happen is that when peer manager actor is started, we both create a listener, a server that listens for incoming connection, and we start several processes in background. The most relevant process here is monitor peers, which will be checking that we have enough peers and health of peers we currently have. Other processes we can dig into them, but are less relevant right now. So let me start for the incoming connections. When we start the server, we just add it creates a stream of connections. Like whenever a connection is created, it triggers the following function handler. Like in Actix, all the main events are triggered via this handler trait, which you can implement for an actor. So in this case, we have this handler inbound TCP Connect, which is a stream. Whenever a new connection to us is created, this function is called with relevant parameters. So here we will check in this function if we can actually establish the connection. We have certain criteria to establish a connection, and if it is fulfilled, we try to start it. Basically, let me step aside from the code. Like the idea is that we want to have so for a node to be healthy, we want to have a certain number of connections, which basically we don't want to pass above some number, because it's hard to maintain let's say hundreds of connections. Right now, this number is 40, but at the same time, because this system is decentralized, we want to avoid a certain type of attacks, such as Eclipse attack. We want that the number of outgoing connections created by ourselves, is above certain number. So for the moment, for accepting a connection, we just check that the number of active peers plus the number of outgoing peers is less than the maximum number of connections allowed. These are peers where, as it says, this is a set with all the peers which we are currently connected to them, and these are peers which we are in the process of connecting to them. So yeah, okay, let me go back a little bit. So if this function is okay, we try to connect to the peer. Otherwise, we just reject that connection. Right now, we just close the port, but eventually we should drop the connection gracefully. So this is how incoming connections are created. For outbound connections, let me go to, in this process, in monitor peers, which is a process that is running in the background. As you can check here in the end of this function is called itself again after some timeout, which increase exponentially, and after some time it just run every some period of time. This is done because we want to start fast connecting to several peers. So in this function, we check for the health of several of nodes. We check for nodes that are banned and should be unbanned if some time span already passed. But most relevant, I wanted to share with you, is that if the node requires some outbound connections, like this is like total number of connections. This is like the idea here. This is kind of complex if like the main idea is that we want to have a certain number of outgoing connections. That is that the number of outgoing connections is above some level, but at the same time, we want the number of connections to be in some range, because nodes will be connecting and disconnecting between each other. We will keep a range of ideal number of connections, which right now the default is 30 and 35. So if the number of connections is in this range, we will try to create. So if the number of outgoing connections is below the minimum outbound peers expected, we will try to create a new connection, but of course always satisfying the maximum number of connections and the ideal number of connections. But let me the point of having this ideal connections range, which is determined by ideal connections low and ideal connections high, is that we want the number of connections be between some range, so that we handle the nodes connecting and disconnecting between each other to be some smooth process, that it's not chaotic and always happening. And we leave some margin here, so that when a new nodes try to connect to the network, there is some margin. So the connections will be accepted by some peers, but the idea is that when the number of connections is above this threshold, the ideal connection high, we will eventually drop some of the connections using certain criteria that we can discuss. Let me show you the function, and then maybe later we can discuss how this is done. Monitor peers. So here we check if there is if we need an outbound connection, we just fetch some peer and try to start a connection. This is happening in this line. We sample a random peer here from peer info, and then we just call the function notify that will try to start immediately an outbound connection. This is, you can check here, handler Outbound Tcp Connect. This will try to start a new connection. So just to finish the, I went too far. Moment. Here, regarding the ideal number of connection, if within the ideal number of connection is above some level, we try to stop some connections. And here we have, this is a function that implements several heuristics to select which connections are preferred over other connections. Like older, we try to reserve, like to keep connections to older nodes, because those are connections that have been more important, in the sense that we know they probably will last longer, but at the same time there are other criteria, such as we want to maintain outbound connections, since we need to avoid, we should try to avoid being eclipsed. And for example, when nodes are archival nodes and they connect between each other, we try to keep those connections because connections between them are very heavy, like the traffic between them is very heavy, and we try to keep connections between them which are basically created manually. So yeah, this is like long lot of heuristics that we might discuss if interested. So let me check. I am not seeing if there is. Okay, there are no questions in chat. Not sure how to see it.
Yeah, let's see if people have questions now is probably a good time to ask. So yeah, for the material we have covered so far.
I guess there are no questions. Okay, just can you please type something in chat so to check how it will appear in my computer, so I'm aware. Okay, something happened. I see. Thank you. Okay, let's go to how connection between peers actually happen. Initially, when a peer connects, when a peer is started, when a node is started, well, it creates this incoming server, but of course nobody will be connected if nobody knows about this node. So the node to connect to other nodes in the network will start with a bootstrap list of nodes, which you can find in this process of monitoring peers. Is outbound bootstrap needed? This, of course, will be true when you have no connections, and then you will start to sample random peers from the peer store, which is populated when you are when the peer manager is started. We take a bootstrap list of nodes, which probably lives here in network config. As far as I remember, we have.
Yeah, it's boot node screw up.
Is it here? I have. Okay.
Yeah, boot node. Yeah.
Boot nodes. Okay, here we have already a list which is loaded from JSON config. This populates the peer store with some. Here we have some logic about how to maintain peers in the network. Most of the logic is to keep this persistent and safe from peers that try to attack and impersonate other peers with invalid IP addresses and ports. But the point is that we store all peers here, and then we sample from the peer store. Okay, so basically what will happen is that when we are trying to create a new connection, either if it is incoming or outgoing or outbound connection, inbound or outbound, we call this function try connect to peer, which have part of the information we need. For example, when the connection is incoming is inbound, we don't have yet the peer information or edge information. Okay, probably at this point, I first want to discuss about edges before starting discussing about how peers connect to each other, because like we will talk about handshake made between two peers, but first I want to talk with you about edges, which are basic data structure that is created for every edge that is created between each peer in the network. When two peers connect to each other, they create an edge, which is later propagated, and it's the way that peer nodes that there is either that there is a connection or that there is no connection between some peers. Like when two peers start a connection, they store their peer IDs, these nonce, which is the complex part here. I will come back right now. Both peers syncs this edge, and then we have this removal info. Like the idea is that if the nonce is an odd number, this edge means that it's a active edge between two peers, and when it is an even number, this means that the edge is about removal, that there is no longer an edge between two peers. So other nodes will only trust, of course, for edges that contain valid signatures, and they will only care about higher nonce, edges with higher nonce, and they will know if they are being created or deleted by the parity of the nonce. If the edge is removed, if the edge is removed, we also need a signature from the peer that removed the edge that needs to sync the full edge. So this sorry, let me come back. This signature here is signing these three fields: the peer, both peer ID and the nonce. These are signed by the signature, and this signature here will be only present if the nonce is even, and will sync the same information. Okay, so but only one peer is required to sign a removal edge. Okay, so that's what edges are. Edge info is just partial information, just the nonce that is being proposed and the signature from the peer that is proposing the edge. So this will only be present when on inbound on outbound connections. When we create a connection, we propose an edge info, like a nonce, and we already signed it, so we can start the process. So when we call this function try to connect, we made several checks, and eventually we start a peer. So basically we will have a peer actor for every active connection that exists, either if it is active or it is in process of being created. Okay, so let's go to peer here and let's analyze what's going on in this place. Like this is again an actor from Actix, so same thing applies. First, when it is created, it's called the new, but nothing is happening here. But there is this function started, which is the function is first called initially. So like eventually what will happen, these are some metrics: fetch client chain information. This is a function that will communicate with the client probably. Yeah, so we have some pipes between every actor, almost every actor in our code. Like there are pipes that connect peer manager with peer, peer with view client, and peer manager with client and view client. All of those are actors, and we have some pipes that allow us to communicate between them. And this is already provided by Actix, all these functions. So what will happen here is that if we are an outbound connection, we will, so if the peer is outbound, we will send the handshake. So notice, let me go here, just a minute. So here in the Outbound Tcp Connect, this function will be called when we try to establish connection from other peer. We will eventually call act try peer connect. We'll call it with outbound. We already have some message information, some edge information, which is computed here, the proposed unknowns. Okay, so only when the peer is outbound, we will try to send handshake. This is to avoid sending double handshake within each other, which actually might happen if both peers try to establish a connection between them at the same time. This is something that might happen, and it's already handled here. So let's discuss what will happen. So the most important function here in PRS probably it's this.
Marcelo, sorry to interrupt. I think it's probably a good time before getting to that part to ask the to answer the questions that people have.
Oh, sorry. So why have the second signature in option? Okay. So the idea, let me go to the code. So the idea is that the first signature only covers for the case when the nonce is odd, and this signature is when the nonce is even. But there is a caveat why we cannot reuse the field, because a node should only propose a node should only propose a removal over a valid created edge. You should not propose a removal on top of an invalid active edge. This is to avoid, like the problem that we are covering here, is that a malicious peer tried to bump this number, the nonce number, much higher and create overflow. This number is not checked for overflow, or this number is not checking overflow. An honest node should not, for honest node, this should not be a problem, very likely, because this number will be bumped in 1 for every new connection that is created. So basically we need these two signatures to check that the created edge is valid, and then this signature to check that the removed edge is also valid. So this signature will be always will be signing odd numbers here, and this signature will be always signing even number. This boolean here is to know which of the parties is signing the removal, either true if it's the first peer or false if it's the second peer. Does this answer your question, Evgeny?
Though it would have been sufficient to reuse the signature of the peer who's removing, right? Because you can sign on the signature of the other peer, right?
Well, we can reuse not the other peer, but our own signature. You say?
Right. So the idea is that right now the removal signature signs on both of the signatures for on the odd nonce.
Yeah, that's correct, because
while in reality it's sufficient. So let's say without loss of generality that the peer 0 is removing the edge. It's sufficient for peer 0 to sign on signature 1, and then we can reuse signature 0 to store it.
Yeah, that's absolutely correct. We still need to store the bool to know who is signing what, but yeah, we can reuse one of the signatures. We use, yeah, you're correct. We only need to store the signature from the other peer that is being created. Okay, this is something that we can optimize. So next question, the signature. Oh, okay, this is the same. Is answering. Signature that to edge is the signature of the creating of the edge. The signature in the option is the signature of the removal. Okay, this is answering the question. So going back, we were going to discuss about starting connection. I'm not in the right stream handler. Okay, here. So in the PRS, I already told that peer are an actor, and this is probably the most important point of the peer, where most of the where the logic starts probably, which is the stream handler. This is receiving information from the network. Before starting here, let me discuss something. When the peer is created, probably in peer manager, peer new, we started, okay, this is happening here. We started with a codec. The codec is like the when some stream of bytes arrive, they first hit this codec, which is implemented by us. Basically, this codec will handle some corner cases, but it basically just read len, expect that the buffer is full, that contains the full message, and then just pass the message completely to the peer itself. And the message that will be received here will be basically the full stream. Okay, so this is the vector of bytes received and decoded by the codec. It's done. It's doing very basic operations there, and we have this logic reason for ban in case some peer will try to send a message that it's too huge, too large, like 1 gigabyte. I don't remember what's our current limit.
Yeah, it's 512 megabytes. Yeah, it's
500 megabytes. Yeah, it's pretty large right now because we are sending chunks and well, chunks not yet, but chunks are pretty large. Okay, so well, we first try to parse this message, to deserialize it. This message is serialized with Borch, and we try to deserialize it. This message will be of type peer message always. Like this is the main data structure that we use to send message through the network. All type of data structures that need to be sent are subfields here, might be very deep. So most of the fields exposed here are relevant for networking, like at least up to this point, these are basically about networking mostly. All those that start with prefix block are more about consensus, and there are a particular type of message that's very relevant, which are routed message, that we will be discussing them probably in next session. So here let's discuss how Handshake works. We have like this state machine for every peer. Like this code already passed it. We just deserialize it. There are some type of failures that we try to address here if the handshake fails for some reasons. This is kind of complex, mostly because when we handle protocol updates, sometimes when the handshake itself was updated, it was kind of hard to handle that case. Not hard, but complex. So that's where all this complexity comes from. So yeah, let me jump up to this place, which is the relevant part. We keep for every peer its status, which is like some sort of state machine. Either we are connecting, it's ready, or it's banned if it's maybe misbehaving for some reason. Right now, the only reason we are banning is for abusive peer that sends more than some amount of transactions of bytes per second. So here, let me try to go over each step. And like initially, well, for handshake failures, when we send something that it's invalid, we will, like the other peer will return some handshake failure with the information that failed, and probably the information that it's required to send the correct information. We can fail for several reasons: genesis mismatch, critical version, invalid target. For example, this invalid target is when we try to connect to a peer and we believe it contains like some peer ID and some address, and that's not correct. That's no longer the peer ID that is running in that address, which is something that might happen if a validator like turn off the node and start with different address. This will be this part of the code will probably be hit. So when we are connecting and receive a handshake, notice that a handshake is sent automatically when we create a connection and it's an outbound connection. So we automatically we automatically send a handshake. Let me show you where it is sent, because okay, here send handshake will just create the handshake. This also has its complex code because it's handling protocol version. Probably we will want to clean part of this code, mostly because the more hard to do upgrades were already done. We are already like we can do upgrades easier now, and we can simplify this code probably. And when the handshake is created, we just send it over the network, and this is the main function that is used to send messages directly to another peer. Okay, we just need to wrap the message inside this peer message, and we just send it to the other party. So going back to the state machine. So when we receive a handshake and we are connecting to this peer, this is actually the first state in which we are in the state machine. We are initially connecting to a peer. When we receive the handshake, well, we process it. Let's discuss what's the information sent in the handshake. We just have version, all the supported version. This is also for upgradability. Some information about us, information about the peer we are trying to connect, and listening part. This is about us as well, and this is information about the chain. This is relevant to avoid peers on different networks connecting to each other, and it also contains some relevant information about us. And this is the edge information. This is partial edge, which is sent when we try to connect to another peer, which will be used to produce the final edge eventually. Okay, we have several checks that verify the handshake is correct. In case it is not correct, if there is no way this can be fixed, we just call context stop. This is part of how actics work on actors. We have access to this context, and if we call stop, basically it will stop this actor from the async pool, and before fully stopping the node, it will call the function not stopping. Yeah, it will first call function stopping, and when this function ends, it will call function stop it. This function, well, we use it. We have some logic here regarding metrics, but most relevant, we also communicate to the peer manager that this peer is no longer an active connection. If it ever was an active connection, we just let the peer manager know in this code. Okay. Oh, I went too far. So we check the edge is valid. We only check partial edges here. If it's invalid, we ban. Oh yeah, I forgot. Of course, we always ban peer for sending invalid crypto. Whatever, if something is wrong with crypto, which we expect it doesn't, because like, well, we don't expect it doesn't. We just ban everyone which sends invalid crypto. This here is like we need to check that the nonces are correct. Like if we propose a nonce, like we have this complex logic that allow both peer to agree on the same nonce, and that this nonce is greater than the previous nonce between them. Like right here, we just check that the nonce we will be using is the one we proposed, because if the peer type is outbound, we just send a handshake and we are receiving the second part of the handshake. We check this is correct, and we then just create peer information, and most importantly, when everything is passed, we consolidate this connection. This will happen if everything with handshake was correct. We consolidate the connection, which eventually will trigger sending the handshake if the peer is inbound. Like if the connection was initiated not from us but from the other peer, if the peer is inbound, when the connection is consolidated, we check the handshake. In the peer manager, well, you can check all the events that might be triggered with handler, as I already told. In particular, this event is consolidate. We need to send this information to peer manager because peer manager itself contains important data structures that needs to be updated, and also that are checked to be able to check if that connection may be consolidated, if something is violated or not. Here, well, again, several checks that everything is correct, that we're not connecting to some blacklisted peer, that we're not connecting to some banned peer, active peers, that we are not connecting to a peer that we are already connected to. This in particular is addressing the case when two peers start to connecting each other. We need to disambiguate. We need to keep only one of the connections, and right now we just compare peer IDs. It's just some arbitrary disambiguation between which connection we will keep, and one of the peers will drop the connection, and the other will will progress, and eventually will succeed. Well, if inbound is not allowed, we will not accept nonce to be zero either. So yeah, there are several checks that needs to be done. In particular, this is interesting because this will trigger another part of the state machine. When the last nonce that we know is greater than the nonce proposed by the other peer, we will reject. We will not fully reject the handshake, but we will reject that proposed nonce, and instead we will propose a higher nonce, because otherwise that connection will not be valid and will not be used by the rest of the network. And this is addressed like when we this is the response. If you're familiar with haptics, we handle the response here. Sorry, I moved. We handle the response in this place. So when we send the consolidate, if it is an invalid nonce, we have a special type of message which is called last edge, and then we send what we send the last edge that already existed within us. Notice that we send the full edge so that it can be verified that it is a valid edge. And when a peer receives the last edge, if it is indeed correct, if it is indeed has higher nonce, we just updated everything. Like we resend handshake again. You can check it. This is another step of the state machine. Like if we receive last edge, we verify everything is correct, and then we propose again the handshake, but with higher nonce. Notice that there is some case that it's not explicitly handled in this state machine, which is when both peer, for some reason, let's say they keep their identities, but they lost all the data. So they lost the higher nonce they had between them. So they will start a new connection with nonce 1, but there is a chance that the higher nonce already existed. So in this case, they will learn it from other peers in the network. We haven't discussed this yet, but we'll probably discuss in the next session. When they learn that they're not the nonce of the edge between them has higher nonce, they will trigger this process of updating the edge. If it they trigger the process of updating the edge, and if it fails, they will disconnect from each other, and maybe they can start to a new connection if they do not update timely the new nonce. So, well, yeah, basically here it's this is the most important part of the connection. It's happening in this part of the state machine. When we receive the handshake, we check everything is correct, and we call consolidate on the peer manager and send handshake again if we are inbound. Send handshake to the other party. Okay. So, well, we already have some other we handle other type of incoming messages, but only when the connection is ready, which is only updated at this point when the connection was consolidated correctly. We mark the connection as ready, and then we start processing other types of messages. Otherwise, those messages were just discarded. So, well, disconnect is used for gracefully disconnection. Handshake is ignored at this point. Peers request, well, here I guess I can talk about discovery of the network, which basically I told we start with a bootstrap node, and then we use send this type of message, which is peers request, which asks for what are healthy known peers for the other party. And when we receive this type of message, we just collect some healthy peers we know. This is done peer response, peers at this response. Okay, peers request. We ask the peer manager for peer request, and in the answer, it will contain all the peers. Notice it's hard to navigate for this code in Actix, because you cannot navigate like this. You need to peer request here. This will ask for healthy peers, and then we'll return the list back to the peer itself, which will be later sent to the peer that asked for more peers. So this is when we receive more peers, we just try to add them to the peer manager. It already has some logic to add new peers. We here have also some protection at the peer store level to avoid cases when some peer try to impersonate others, like try to claim that an IP is controlled by a peer with different ID or something like that. Those cases are addressed here in the peer store. There is also some complex logic because of that. We have like some trust level on each case, which can be indirect, direct, or signed. Indirect is when we learn it from other peer. Direct is when we learn it from the peer that control that address. It's coming directly from that pipe. And signed is when we already have some message signed by that peer ID with the private key, so we can be sure. To understand the logic, probably the best case will be to check these unit tests that try to cover all the cases.
Hey Marcelo, I want to mention that we should be a bit mindful of the time here. I think we're almost
yes,
at 1 hour.
Yeah. I'm seeing the time. We have 7 minutes to finish, and I will just try to finish quick this state machine, and yeah. But well, probably you can in what now that you understand how like the main logic for interacting with other peer works, you can probably inspect the rest of the of the state machine. It handles each type of connections most of the time, communicating to the peer manager to resolve some of this information. So well, here is when we try to update the nonce that I was talking before, and the rest of the message are relevant either for routing between inside the network when we try to route a message to another peer directly. This is for fast propagation of certain type of message, such as transactions and chunks, and in particular some general type of message are just handled by this function receive, which propagate that message either for the view client or for the client, depending on its type. Okay, so well, I just finish here for now. In the next session, we can try to cover all the logic regarding routing the messages. I think we covered some of the essential part of the connecting to each other. So if you have any questions in these 5 last minutes. Okay, I guess we're good.
Okay, so no one has questions. Okay, I guess then we can end it here. And yeah, thanks Marcelo for doing the walkthrough. And I think we'll have another session on Monday next week, where Marcelo would be talking about how messages are routed in the network. And yeah, thanks everyone for joining. And again, thank you, Marcelo.